When we're talking about the time complexity of a single loop or a function like Fibonacci or factorial, we've only got one thing we're looking at. We're looking at that one function call, that one loop, and we're saying, how long did it take? When we're looking at data structures that persist over time, often this kind of analysis is less useful. Instead, we're required to look at a sequence of operations in order to understand how the data structure is going to perform. The tool we're going to use here is Amortized Analysis. What this allows us to do is to look at the cost of a sequence of operations rather than looking simply at one operation in isolation. If you've ever used a loyalty card at a retailer, you know what this is like. I go to Starbucks, after 9 coffees, I get one free. It may be more compelling to think of a super loyalty card. Let's suppose normally I get a $3 coffee at Starbucks and they give me a deal, which is that they're going to say, well, look, you buy one coffee for $27 and then we'll give you 9 for free. And if you think about it, that's a good deal. I'm still getting less than I would be paying for 10 coffees at $3 a coffee. That would be $30 and I'm getting them for 27. So the amortized analysis I can make is, as long as I'm going to keep buying coffee, that's a good deal. We're going to look at 2 examples of this kind of amortized analysis. The first is resizing arrays, and the second is building strings. If you remember back when we talked about stacks implemented inside of arrays, we had a little issue there, which is that the stacks were fixed capacity. That's not great, and that led us to come up with a linked structure to represent a stack. But there is a way to represent a variable length stack using arrays. What we simply need to do is to occasionally throw away the array we have and create a new one. Of course, that's going to incur the cost of copying the contents of the old array into the new one, and we need to take that into account as we analyze the code. Here's something that does exactly that. My stack here is called performance of arrays. I have an underlying array A, which is going to store my data, a count, which keeps track of how much of the data in the array is significant, and I'll initialize those to have just a single element in the array, which is not significant. And my push method here is going to simply take the item that's being pushed and store that in the array at element in. And then, of course, we increment in. That works fine as long as we have space or capacity in A in the array. But there's a problem here if we run out of capacity. So once in is equal to the length, accessing the array at element in would give me an array index out of bounds exception. And to avoid that, I'm going to call a resize method to throw away that small array and give myself some extra room. What does that look like? I'm simply going to resize to a given capacity and then copy all of the old elements from the old array into the new array. And finally, throw the old array away and update the variable A to hold the new array temp, which is bigger. I've also annotated the code here to do a little bit of printing so we can see stuff, and also to record the number of writes that I'm doing so we can keep track of the complexity of what's going on here. So let's start looking at this where we do in pushes for some large in. And I'm going to start off where when I run out of room, I'm just going to give myself one extra bit of space. So what's that going to look like? How much work do you think I'm going to do in pushes with this kind of strategy? So each time I need a little bit more room, I'm just going to create a little bit more room, just the amount I need. So I'm optimizing space. I'm not wasting space here. I'm only allocating space that I need. That's great. But let's think about how much copying I'm going to do. And in fact, that's what I'm printing out here. It's the copying. Now that copying is not productive. All it's doing is copying the old contents into the new array. So it's really just wasted effort. You can see that push is constant time if you just look at the work that is happening in the method itself. The only more complex thing that's happening is in the resize method. But analyzing resize is quite difficult because in order to understand how long resize takes, well, we need to know what in is, and that varies. So as we increase the size of our stack, in is going to increase. We'll start with 1, then 2, then 3, then 4, then 5. Oh, and so now if we're copying that many times, we copy once, then twice, then 3, then 4, then 5. Oh, how many times are we copying? Well, that's something that's familiar to us. It's a triangle. Look how much we copy. We copy once, we copy twice, we copy 3 times. Once I've got 3 things, well, it's great. I have 3 things in my array, but when I need room for a 4th, I have to copy all those things over again. And all of this copying adds up. We've already done this analysis. We know that if we're going to be doing a triangular amount of work, well, that's actually in squared time. Now note that this is not the time for a single operation. So one push is not costing me in squared time. It's instead doing in pushes. In pushes taking in squared time. Now if you look at the time of each individual push then, you can sort of take the average if you like, and it's in or linear time. And this is borne out experimentally. You can look at the wall clock here, and for 260,000 elements, it's taking 40 seconds to push those 260,000 elements into the array. And why is that? It's because I'm doing this ridiculous amount of wasted copying effort. So the first thing you might think is, well, why am I just giving myself 1 space? Let me give myself more space. Let me give myself 10 extra spots. Surely that's going to be better. And it is for a little bit. You can see I actually get, well, 10 times better performance. In fact, for 260,000 elements, instead of taking 38 seconds, it's taking 3.8 seconds. So in fact, almost exactly 10 times faster. And you can also see that in the sort of output here. So instead of getting that big triangle, I'm getting a flatter triangle. The point is, though, this is still a triangle, and the sum is still, unfortunately, quadratic. And you can see that borne out both by the annotated code, where I'm counting the number of operations, and also by the wall clock. So for 260,000 elements, it's still taking 4 seconds. It may seem at first that this is sort of like my Starbucks card. I pay for 10 pushes up front, and then I get 9 for free. The problem here is that the cost of that 10th push keeps going up because there's more and more things behind me. It's like when I go into Starbucks, they don't just charge me for the 10 coffees I'm about to have, but they also charge me for every coffee I ever had before. So I go into Starbucks, it's $10 this week and I get 10 coffees. Next week it's $20 and I get 10 coffees. Next week it's $30 and I get 10 coffees. And that cost is going to keep piling up behind and drags everything to a grinding halt. And it doesn't help to make it 100 either. 100 free coffees sounds great. But the thing is, if those coffees keep getting more and more expensive, eventually the coffee's not going to be worth it. And here, indeed, I'm doing those 260,000 pretty fast now, but still, I can't really scale up to larger problem sizes. So here, 99 constant time coffees for one that's got a cost that keeps going up. I'm still at amortized linear time, so each of these coffees is actually costing me proportional to the total number that I ever had. So what can I do? Well, we can be sort of informed by our analysis of loops. So we noted that the triangular loops had this kind of quadratic performance. We got much better performance if we had the flat pack loop. And what did a flat pack loop look like? Well, I double the amount of work each time around, but overall I do things fewer times. And I can do that in this code by resizing by multiplying by 2. So if you think what's going to happen here, the first time I run out of room, I copy 1 element. The second time I copy 2. The third time, instead of copying 3 elements, I copy 4. After that, the fourth time I copy 8, the fifth 16, and so on and so forth. And what that means is that I do a lot less copying. I know that this looks kind of like a triangle. This is not a triangle. This is a swooped down flat pack in the sense that I can take all of the things here on top of the bottom row and pile them up right on top, and I just get something too deep. This is not a triangle, and that is borne out experimentally as well. You can see here for 260,000 elements, oh, well, that's still fast, but look how much I can do. I can now get up into 60 million elements in still less than half a second. And this kind of performance is something I wasn't even getting close to with my additive solution. For 2 million here, it's taking me 30 seconds. For 2 million here, it's taking me nothing. So by doubling the array size each time, I save a huge amount of work overall. The total time for in operations is about 2 in, and therefore each individual push is amortized constant time. This is a huge win. And if you're winning with 2, you might think I'll win better with 4. You can do a little bit better, I guess. Let's see what the absolute numbers look like. For 67 million, I'm getting half a second. Well, let's see what's like with 4. Well, for 67 million, I'm getting about half that. Okay, that's nice. What if I go up to 8? Well, yeah, it seems to have bottomed out, actually. I'm not getting that much better. In fact, it may be slightly worse. It doesn't matter what the multiplier is. What matters is that I'm multiplying. And that's what gives me the ability to flat pack these sums. So the work is spreading out, if you like. If you think about it, the amount of copying I'm doing is much larger, but I get more free things afterwards. So here it's like I'm going into Starbucks and it's like the first time the card is $10. I have to go to $1 copies because I can't multiply by 3 that fast. So the first card is $10 and I get 10 coffees. The second card is $20, but I get 20 coffees. Then the next time I go in, I have to pay $40, but I get 40 coffees. It's not really that dreadful. So you can see that the amount of free stuff I'm getting corresponds to the amount of coffees or the amount of copying that I'm doing. And this works even if the multiple is less than 2. 1.5 is a common choice for resizing arrays because the arrays don't grow quite as fast. You may not waste quite as much space, but you still get the rocking performance. And you can see that here. I actually do a little bit more work, and this is looking more like a triangle, but this is not a triangle. This is still a flat pack. The thing is growing. You can see that each layer is sort of longer than the one preceding it, and that's the important quality. And in fact, you can see the numbers sort of bear out here. In this case, the numbers are going up and down and up and down, up and down, up and down. And it can be a little confusing to see what's going on. The reason for this is that sometimes we have over allocated and sometimes we've under allocated. And so the cost is sort of varying a bit. So what I've done is I just added up all of these multipliers and taken the average. And you can see that the average delta, the average change from one to the other, is really quite close to 2. It may be somewhat shocking, but in fact, it really doesn't matter what this multiplier is as long as it's larger than 1. So even taking something like 1.1, well, we've got something looking pretty triangular here for a while, but note that after a while, it starts to lengthen out. And that is an important quality. It's enough. It's enough to get the performance that we need. And again, if you look at what happens here, I'm actually getting excellent performance, even multiplying just by 1.1. The point is that the number of free accesses that I get is sort of scaling as I get larger. I get larger number of free or low-cost accesses for larger sizes. The total complexity for in push elements here is right at linear time. You can see in absolute terms that I'm doing about 10 in work to push in elements. If you go back, you can look at the 1.5 solution. You can see I'm doing about 3 in work here. You can see that for 8 in, it's quite a small factor. For 4 in, it's a little bit bigger. For 2 in, it's right at 2 times. So 2 times work for 2 in, 3 times work for 1.5 in, 10 times work for 1.1 in. And you can work out the math in your head if you want, but it's not that important. The real deal here is that if you look at the ratio of one size to the doubled size, it's going to be right at 2. And that means that it's some sort of linear function. It really doesn't matter if it's times 2 or times 10. It's a linear function, and that's going to dominate everything. The particular number that's chosen in implementation is actually a balance of size and space. So if we choose a larger constant like 8, well, we might be wasting a lot of room in the computer. If we choose smaller constants, we will waste less room, but we do slightly more work. So we can decide whether we want to have a little bit more in terms of the operations or a little bit more in terms of wasted space. That's the trade-off. Last time I looked at Java's ArrayList class, it was tuned to right at 1.5. So this is how a resizing array is used to implement something like a stack. If you want to see a more fully fleshed out example, you can look at the resizing array stack class in the algs1.3 package. This is a fully fleshed out sort of example where we not only increase the size when pushing, but also potentially decrease the size when popping so as to avoid wasting space. You can also see a similar implementation with the resizing array queue, also in the algs1.3 package, where again, enqueue and dequeue may both cause the array underlying the data structure to get resized.